Okay, hi everybody. So I'm going to talk about product mixing in compactly groups, and this is joint work with David Ellis, Guy Kinder, and Noam Lifshitz. So what are product presets? Well, given a group G with an operation times, a set of elements A is called the product preset if it does not contain any solution to the equation x times y equals z. In other words, it doesn't contain any element of the form x times y for x and y in A. So let's consider a few examples. Well, let's take an abelian group. Let's take z mod nz with the addition of operation. Well, in that case, we're going to call the product free set a sum free set because the operation is summation. And you can observe that the set of integers between n over 3 and 2n over 3 is a sum free set. And this is also a fairly large set. It contains roughly a third of all of the group. So this abelian group has a very large product free set. Well, let's consider another group, but this time a non-abelian group. Let's take Sm. And the operation is times, or composition of permutations. Well, in that case, you again have a very large product free set because you can take all of the odd permutations, and this will form a product free set because the product of any two odd permutations is even. And the relative size of this set is half. So again, you have a very large set. So this brings two questions. So when does a given group have a product free set of constant density? And secondly, given such a group G, can you actually tell what is the largest product free set looking like? So this question makes sense over finite groups, just like in these two examples, but it makes sense over more general groups as long as you can define size in some reasonable way, and usually this is done via what is called Haar measure. Okay. So in fact, there are notions that are stronger than product freeness that you can consider that are very much related. So one notion is product mixing, which says that not only does a must contain products, in fact, products from it must look kind of uniform. So more precisely, we say set A is product mixing if when you sample two elements xy from it, then the distribution of x times y looks very close to uniform. And product mixing in G would say that any not too small set A would be product mixing. Similarly, you can ask about growth in G. Given a sizable set A, how much larger does the product set A times A have to be? Well, A times A is just a set of elements of the form x times y, where x, y are from A. And thirdly, you can ask about diameters in G. So suppose I give you a generating set A. What is the smallest power k such that A to the k is already the entire group G? So these questions and other notions that are related to it can be seen in communication complexity, for example. So there is the work of Gowers and Viola that study a very nice and natural multi-party communication game that is based on product in groups, and they show relations between product mixing and product freeness to the communication complexity of the players in this game. And secondly, there is the work of Aaron Chalam, Girish, and Lifshitz that use tools that we also use, namely product mixing and stuff like that, to show separation between classical and quantum communication complexity in some specific model of communication. So besides these two applications, there are many other relations and applications to analysis, group theory, and expansion that I'm not going to mention in this talk. And if you're interested, you should have a look at the paper. It explained very extensively. Okay, so it turns out if you want to understand all of these questions, then the parameter that is of most importance is what is called the quasi-randomness of a group. And this is defined as follows. So first, we have to define representations of a group. And in one word, representations are generalization of characters beyond complex numbers. And more specifically, a representation of a group G is a map from the group to linear actions to matrices, which is an homomorphism. Namely, it maps the element x times y into the product rho x and rho y. So, this is a very clear generalization of characters. So if you're doing a billion Fourier analysis, then you use characters, which are maps from G to complex numbers, which are multiplicative. So if you think of complex numbers as one by one matrices, once you do non-abelian Fourier analysis, you have to use larger matrices, and this is where representations come into the picture. So now that we have the notion of representations, we can define the dimension of a representation. So the dimension of a representation rho is the dimension of the vector space V over which the matrices are defined. And finally, the group G is called D quasi-random if all of the non-trivial representations of it rho have dimension at least D. So there is always a trivial representation, which is just map all of the elements to the number 1. So what we're saying here is, besides this trivial one, all of the rest of them must have a large dimension. And in that case, we say that a group G is quasi-random. So this parameter became important in the context of product freeness since the work of Gowers, who showed the following result. So he showed that if you have a group G that has large quasi-randomness parameter, then any product free set in it must be small. And more quantitatively, the relative size of any product free set in G is at most 1 over d to the third, where d is the quasi-randomness parameter. In fact, the Gowers proved something even stronger, that such sets are product mixing, but for this talk it suffices to say that it proved a bound on the product free sets. So, as long as finite groups are concerned, Gowers' bound is tight up to polynomial factors in D. And indeed, you can see that any group G that has a representation of dimension D must have a product free set with relative size at least omega of 1 over D. So there is some gap, but it's only polynomial. And indeed, this gap can be observed for some groups. So for example, if you take the alternative group, then the bound that Gowers gives is 1 over n to the third, but it turns out that the truth is 1 over root n. Now, when you look at infinite groups, then this gap can actually be much bigger. And for concreteness, let's look at the special orthogonal group, which are all of the matrices that are orthogonal and have determinant 1, and we equip this set with the Haar measure. So in this case, Gowers still gives a bound of 1 over n to the third if A is a product free set inside the S1. But in this case, he conjectured that the truth must be actually much more farther than that, and that the measure of any product free set must be at most exponentially small in n. And in fact, if you set your mind to it and think about it a little bit, then there is really only one idea to demonstrate a product free set in S1, which proceeds as follows. So you pick your favorite unique vector V, and you observe that if you take all of the matrices M that map V to negative V, this would be a product free set. Because, if you multiply two of them, then they would be fixed point. The issue is that this set has measure 0. So what you do is you say, okay, let's take all of the matrices V, M that map V to almost negative V. So then you can still show that this is the product free set kind of easily, but now you have some measure, and the measure that you have is actually exponentially small in n. So we suspect that the experimental examples should look something like that, but we don't know how to prove that, and we are not even close to that. And the situation is not unique for SON. It appears for virtually any other compact Lie group, so there is the list here. But for this talk, I'm going to talk about only SON. So now I come to the main result of this paper, which is to improve Gowers bound for compact Lie groups and for SON more specifically even. So we show that if you have a connected Lie group of that is D quasi-random, then the measure of any product free set in it is at most exponentially small in D to the third. And there is some small aspects there because D is not quite the quasi-randomness parameter of the group, but rather of its universal cover. There could be some gap between them. For the groups that I mentioned, there is no gap. So let's ignore these aspects for now. So this theorem is, you see an exponential improvement over Gowers, but there is still a gap between this bound and what is suspected to be the truth, which is 2 to the minus O of D, at least for the group that I mentioned previously. And in fact, 2 to the minus O of D is the best you can do because Gowers' argument from finite group extends to infinite groups, but in that case, you don't get polynomial in 1 over D, but rather exponential in D. So we can show that if you have D quasi-randomness, then there is always a product-free set of measure which is exponentially small in D. So I'm not going to read all of these results. What I'm trying to say here is that, in fact, we not only talk about product-free sets, but we also talk about these more refined notions of product mixing, expansion, diameter, and so on. And we can even give interesting eigenvalue bounds on Cayley graphs of non-trivial sets in the group G. So you can look at the parameters that are here, but basically the moral here is that as long as your set is not abysmally small, it's going to be product mixing, it's going to have constant diameter, and so on and so forth. So that's that. Well, so how do we prove all of these things? So the main technical contribution of this work are new hypercontractibility inequalities for compact Lie groups. And once you have that, all of these results that I said follow from kind of well-known arguments. So I'm not going to say anything about that. And for the rest of the talk, I'm going to try to give you some hint as to how we establish these new hypercompatible inequalities, and I'm going to focus on SON. So what is hyperconductivity? Well, hyperconductivity is all about low-degree polynomials and their values. And if you work over SON, or let's work over ON, because for hyperconductivity it doesn't matter, you can look at polynomials over it, which are just polynomials in the entries of the matrix X. And the degree here is pretty much what you expect. It's just the degree is a polynomial. And once you have polynomials, you can measure norms of them. So you can define the Q norm of F, which, if you raise it to the power Q, is the expectation of Fx to the Q when you sample X according to the Haar measure over ON. So hyperconductivity, or namely what we want to establish, is an inequality of the form that the Q norm of a low-degree polynomial F is not much more than the 2 norm of that polynomial F. And I'm not going to get into the details of exactly what this bound is like, but for us, it's important to get the right quantitative dependency on the norm Q as well as on the degree F. So it's really important for us that we are going to get this comparison between norms of this form. And if you ignore these quantitative aspects, what hyperconductivity is about when you formulate it like that is saying that if you look at the low-degree polynomial F, the probability that it gets very large values is very small. And this is because if you look at very large values, they contribute much more to the Q norm than compared to the 2 norm. So therefore, if f got very large values, this sort of inequality would not hold. So you can expect stuff like that to be useful, and indeed it is. So what's the issue here? Well, hyperconductivity is known for a whole bunch of spaces, and you can try to establish it via several ways. But none of them, as far as we know, works in the case of ON, because ON is not a product space. And if you try to expand something like the Q norm, then you're going to run into many terms, and they're going to be hard to compute because the entries of ON are dependent, right? Because any two columns in ON would be orthogonal, and the 2 norm of any single column would be 1. So there are dependencies which make this computation of the norms very difficult. So indeed, we have to do something else if we want to establish hyperconductivity, and this is the main contribution of this work. So to get some intuition, let's look at an input matrix X, and let's look at a small minor of it. So here is the wishful thinking. The dependencies that we outlined for the metric X, they are all high degree looking. And the hope here is that if you look at a small minor of X, then the entries should be roughly independent. And moreover, each one of them should basically be a Gaussian with mean 0 and variance 1 over n. And again, this is because when you look at a small window, you don't expect to see this correlation. So, and once you remove the correlations, this is what it should look like. So this gives you the hope, or at least the idea to try, which is to reduce to Gaussian space. Because you could hope that maybe the worst low-degree polynomials that you need to argue about are local polynomials, namely polynomials that look at these small minors. When you look at these small minors, it's pretty much the same as Gaussian space. And on Gaussian space, you have everything that you want. So indeed, if we can make something like that work and do a reduction to Gaussian space, then because we already know hyperconductivity on Gaussian space to be done, but the question is how to do it. And it turns out this intuition is true and can in fact be formalized, and this is done via coupling with Gaussian space. So I'm not going to give any details about this coupling due to lack of time, but I encourage you to look at the paper if you're interested. So the coupling approach that we gives the best quantitative bounds, and if you want the bounds that I stated in the beginning of the talk, you have to go through with that. But the two downsides of it is that, you know, to make it work, you require quite a bit of work and actually use quite a bit of stuff like representation theory and some nice facts from there. And the second downside is that there is some sweet spot up to which it works, and beyond that, it doesn't give anything. So this coupling-based approach works for polynomials of degree up to root n for ON, and once you go beyond root n degree, you don't get anything. So this is kind of annoying, and you know, in some sense, the reason for that is that when you go beyond d by d minors, when b is larger than root n, then this intuition of the minor starts being true, and there is no hope for this, or at least as far as we know. So in the paper, we also show an alternative approach to hyperconductivity, and this approach is based on Ricci curvature. So the main advantage of it is that it's more generic and it gives you a result for any degree that you want. But the main disadvantage is that it never quite gives you the best quantitative results. So you can get some results along the lines that I stated earlier, but they would all have worse exponents. So what happens between root and over n? Well, we don't really know. So we know that beyond degree n, basically what you get from the Ricci curvature-based approach should be the truth, up to, again, some constants. But between root n and n, we don't really know what should be the case, and maybe there is some third approach that addresses this case. So this would be interesting to study. So in conclusion, in this talk, we talked about hyperconductivity over compact Lie groups, and we said that there is a hyperconductivity result which is optimal for not too high degrees, and mentioned some applications to product freeness and other notions of mixing in groups. So as open questions, it will be interesting to see other applications for it, let's say from communication for complexity, or maybe from quantum computation. Well, in quantum computing, it's all about unitary matrices. So UN is all in there. And it would be reasonable to expect that if you have hyperconductivity over UN, then you should be able to use it to do some things. And secondly, it would be interesting to close the gap between 2 to the minus n to the third and 2 to the minus n for product-free sets in SO1, as well as understand what should be the behavior of hyperconductivities for functions of degrees between root n and n over this domain. So that's it. Thanks.